In this video, we're going to start looking at where the electrons are in our atom. And the model that we're going to use is quantum mechanics, or the quantum mechanical model of our atom. In the last set of videos, we did talk briefly about the Bohr model. Remember, we said that Niels Bohr was the first to propose a model of the atom where the electrons were constrained to specific energy levels. He then had those electrons just going around in the orbit. That's what he called those energy levels, kind of like a planet would orbit the sun, right? It was based on planetary motion. We do know that particles do exhibit, right? Matter can exhibit wave-like behavior also. And this is what the quantum mechanical model is based on. So based upon the wave-like properties of an atom, we did calculate the wavelength of our electron using the de Broglie equation a little while back. So we know that electrons do follow a wave-like pattern. And this should actually say the wave-like properties of an electron, not an atom. Sorry, guys. So if we looked at Bohr, right, we have our nucleus in the middle, and then again, totally not to scale, I have these different energy levels. And according to Bohr, our electron is just circulating, right? It's just going around in a circular pattern in that energy level. Of course, we can add energy to it and bump it up. It can lose energy and go back down, but within an level, right, it's just going around in a circular pattern. What we're saying here is that our electrons actually follow a wave-like pattern instead of going in a circular manner. And when we calculated the wavelength of our electron, it's actually greater than the diameter of a hydrogen atom itself. So you can't really see it going around. It kind of looks like it's jumping. It's here and then it's here and so on. So again, based on the wave-like properties of our electron. It's not following some sort of defined path. In fact, the path is very undefined. It is a mathematical model. And it's in the form of the wave equation. The solutions to the wave equation are our orbitals, and our orbitals are going to be defined as the region of space where we're likely to find that electron. So our orbital, also called a wave function, given the abbreviation capital psi, and these are the solutions to the wave equation. So we have a big mathematical equation called the wave equation. We solve that equation. The solutions are my wave functions, also known as orbitals. Orbitals is probably the term that you've heard before. So an orbital is just another name for a wave function. Wave functions are the solution to my wave equation, which is the big math equation that this entire model is based upon. If we were to define again that orbital, it's the region of space outside of our nucleus where an electron is most likely to be found. And we say most likely, we don't know that it's there for sure. It is a probability. If we were to actually square psi squared, it gives us the probability of finding the electron in that specific region of space. So it defines the probability of finding an electron in that specific region of space. Our wave function, psi, contains 3 variables. And these variables are called our quantum numbers. there's actually going to be 4 quantum numbers. we'll add the fourth one after, but for now I just want to talk about these first three. So psi contains three variables. These variables are our quantum numbers, and they're going to define the energy, shape, and three-dimensional orientation of the orbital. So what is the energy of the orbital? What is the shape of the orbital? And then how is that orbital oriented in three-dimensional space? So that's what our quantum numbers are going to define. Our first quantum number, so we're going to go through our quantum numbers here. Our first one is our principal quantum number. And we've actually already used this one. Our abbreviation for our principal quantum number is a lowercase n. And n is going to define the orbital's energy, and then essentially its size, its extension into space. Remember, if the electron is closer to the nucleus, it's lower in energy. If it's higher, it's higher in energy when it's further from the nucleus. So the more it extends into space, the higher its energy. The less it extends into space, the lower its energy. So when we define its energy, we're also defining its size here. So my principal quantum number n, this defines the extension into space of the orbital. And thus its energy. So when I draw those little cutaway pictures of our atom, right, I could have an electron here, or an electron here, or an electron here. As I go in this direction, right, it extends further into space, right, so it's higher in energy. Often a principal quantum number, or our value for a principal quantum number, is called a shell. So it defines our shell. Sometimes we'll use the word energy level. So shell, energy level, values for n are all the same thing. So this is my first energy level, it's my first shell. This is my second energy level, it's my second shell. My third energy level, my third shell. As your value for n gets bigger, it extends further into space and it's higher in energy. Mathematically, n is always a whole number integer. So it's a positive whole number integer. So n is always going to be 1, 2, 3, etc. N is never going to be 4.76 or -2. It's always just going to be a positive whole number. So energy, I didn't write it down, but we do have this here, right? Energy is increasing as my value for n increases. So the energy increases as the value for n increases. Our second quantum number is our angular momentum quantum number. And its abbreviation is a lowercase l. I usually make it cursive, because if I make a lowercase l like this, it looks like it's a 1. So I'll generally make it cursive. You don't have to, but I do need to know that your L is an L and your 1s are 1s. So whatever you have to do to make them different. And it does need to be lowercase, so please do not do that, because that's not a lowercase l. So angular momentum quantum number, lowercase l. And what this defines is the shape of that orbital. Orbitals are not necessarily round. There's only one value for L in which it is spherical. All of the other values for L are not round. So when we draw pictures of atoms, like that Bohr one I just drew like this, that's completely not accurate at all. They are not actually round, which is why I generally just do these little cutaway pictures, because I don't want to complete it because it's being incredibly inaccurate when I do that. So it defines the shape of our orbital. Often we'll call these our subshells. So different subshells have different shapes. I'm going to talk more about the shape after we do our third quantum number, because I think the two go together really well. But for now, know that it does define the shape of our orbital. We can say subshells for the different values. And then also numerically, L is always equal to 0, or from 0 to n minus 1. So depending on what shell you're in, right, what your value for n is, you're going to have a different number of subshells, a different number of shapes. So for example, if you are in your second shell, L is going to be equal to 0, right, because it's everything from 0, and then that goes to, let's actually do a comma, goes to n minus 1. Here n is 2, so 2 minus 1 is 1, so everything between 0 and 1. So L is equal to those two. So what that tells me is that in my second shell, right, n is equal to 2, it's my second shell, I have two subshells because I have two values for L. Each of those subshells has a different shape. So in my second energy level, I have two different shapes for my orbitals. So I have two subshells, right? I have two values for L when I'm in that second shell. If I was in, let's say, my fifth shell, so n is equal to 5, L is everything between 0 and then 5 minus 1, which is 4. So L is equal to 0, 1, 2, 3, and 4. So when I am in my fifth shell, I actually have 5 different, because there's 5 values here, right? 1, 2, 3, 4, 5. I have 5 subshells. There's 5 different shaped orbitals, not necessarily 5 orbitals, we still have another quantum number to cover, but 5 different shaped orbitals in the fifth shell. If L was equal to 11, if n was equal to 11, right? If I'm in the 11th shell, then L is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, right? Everything from 0 to n minus 1. And you do need to know these. A very typical question is if I give you a shell number and I ask you what are your possible values for L, or how many subshells you have. So L is always 0 to n minus 1. My third quantum number is our magnetic quantum number. And our abbreviation for this one is a lowercase m with a lowercase subscript L, so m sub L. You do need the lowercase m and the lowercase subscript L. We're going to actually have an m sub s neither. That's going to be our fourth quantum number. So my magnetic quantum number, this is going to be the one that defines the three-dimensional orientation. So how is it oriented in space? Is it on the x-axis, y-axis? What is it, its orientation? So this defines the three-dimensional orientation in space. Each value for m sub L is a different orbital. So this is how we know the number of orbitals we have per subshell. So each value for m sub l is a different orientation, but it's also a different orbital. It's a different region of space for each value you have. So we could say the number of values for m sub l gives the number of orbitals per subshell. I'm saying per subshell because when I give you the formula for determining the number of values, it's based on your value for L. So what that is, my possibilities for m sub l, it doesn't really look lowercase, it should be, is it's going to equal everything from negative L to positive L. So if L is 1, m sub l is going to be negative 1, 0, and 1. Let's actually write that down. So everything from negative 1, 0 is a value, so that does count, to positive L. Remember, the number of values for m sub l gives the number of orbitals. I have 3 values, so what that means is I have 3 orbitals, right? Each value is a different orientation. So I have 3 ways. Remember, L gives us the shape. So I have 3 different ways I can take that shape and orient it in space. So 3 orientations means I have 3 orbitals when L is equal to 1. If L is equal to 2, right, m sub l is everything between negative 2 and positive 2, so negative 2, negative 1, 0, 1, and 2. If I was to count the number of numbers there, there's 5 of them, right? 1, 2, 3, 4, 5. So I have 5 different ways I can orient the shape. So 5 orientations in 3-dimensional space. Each orientation is a different orbital. So I have 5 different orbitals when L is equal to 1. I do want to look at the shapes next, but let's do a quick summary first just to make sure we're together. So quantum mechanics, it's based on the wave-like properties of our electron. It's a big mathematical model. The solutions to that mathematical model, the model is called the wave equation. The solutions are our wave functions, and they define an orbital. An orbital is the region of space where those electrons are, which is what we're trying to figure out. So if we solve this math equation, the solutions tell us where our electrons are. There's 3 variables contained in the solution. Those variables define the energy of the orbital, essentially its extension into space. So are the electrons in that region of space close to the nucleus? If they are, they're low in energy. Are they further from the nucleus? If they are, they're higher in energy. Our second variable, our angular momentum quantum number, defines the shape. We could also say subshell. Different subshells have different shapes. And then our third one, m sub l, that defines the orientation. So how is that region of space oriented in 3-dimensional space? So just again, summarizing, n is my principal quantum number. Right, it defines the energy. We could say size. We can call those shells. I don't use the term shell a lot. I'm more likely to say energy level, but shell is, there's nothing wrong with that term. N is always a whole number integer. 0 is not one of them. So 1, 2, 3, etc. L is my angular momentum quantum number. It defines the shape of our orbital. We can call those subshells if we want. And L is always 0 to n minus 1. And then we had m sub l. That's my magnetic quantum number. it defined the three-dimensional orientation of our region of space, right, of our orbital, and this gives the number of orbitals per subshell. And m sub l is everything from negative L to positive L. The number of values that we get, again, are the number of orbitals we have, the number of regions of space in that subshell where I can have electrons. So I do want to go through those shapes. Oftentimes in these values that I'm about to give you probably look where stuff starts looking a little familiar. Often we use letters when referring to values for L. If we don't use letters, it can be really confusing. If we use numbers for N and numbers for L. So when we're saying where an electron is, we need to give both the energy level, the shell, and we have to give the subshell its shape. And if we use numbers for both of those things, it can be confusing. So a lot of times we're going to use letters instead of numbers for L. So often, letters instead of numbers are used when referring to values for L, when referring to subshells. I use both, so I do want you to know them. You definitely need to know the letters because we're going to be doing that when we start putting electrons into orbitals for different atoms. So if L is equal to 0, my corresponding letter is S. If L is equal to 1, my corresponding letter is P. Hopefully those are starting to look familiar for you from your chemistry past. What is it if L is equal to 2? What comes next? SP. Hopefully you guys said D. If it's 3, my corresponding letter is F. And then after this, it does just go alphabetically. Skipping, of course, S, P, D, and F when you get to them in the alphabet. We actually only have atoms that have electrons up to the F subshell, but that doesn't mean these others don't exist. We just don't have electrons in them, right? Regions of space can be empty. My office right now on campus should be empty, but that doesn't mean my office doesn't exist, right? Remember, these are solutions to a big mathematical problem equation. So in theory, I do have that region of space. We're just not going to put any electrons in them. So after F, it does just go alphabetically. So looking at the shapes, and I'm going to sketch some of these, but I'm also going to refer you to your text on the internet. I'm not a great artist, but at some point I may ask you to draw them. So what I draw, I expect you to be able to draw, and then I expect you to be able to look at pictures of the others that I can't draw and recognize them. So shapes of orbitals. Again, remember it's my values for L that define that shape. And please look up pictures because mine are only going to be so good. So when L is equal to 0, right, that's my first value for L. That means it is an S subshell if we were to use our letters. And then how many S orbitals do I have per subshell? Interpretation, what are my possible values for m sub L? So when L is equal to 0, m sub L is also only equal to 0, right? If we go back up here, m sub L is equal to negative L to positive L. Here L is 0. 0 is just 0. There's no positive or negative 0. So m sub L is 0. What that means is there's one orientation, meaning there's one s orbital per subshell. So for s's, there's only one thing I can draw per subshell. As my shell got bigger, my shape is going to be the same. I'm still only going to draw one, but I'm just going to draw it bigger, right? I'm going to draw it extending further into space. So along our standard set of axes, so my y, my x, and my z, I'm going to have my nucleus right in the center here where they're all crossing. The one that's at an angle is coming in and out at you. So the one that's sloped down is coming out. The one that's sloped up, right, the half that's sloped up is going back. And these ones are spherical shaped. I'm going to use my highlighter, it might be easier to draw it. And they're just centered around the nucleus. So they look like a big ball, right? Not a circle. A circle would imply flat, but a sphere. So anytime L is equal to 0, that shape is going to be spherical. So these are spherical. How my value for L changes in different shells is it just gets larger, right? Remember, if n is equal to 2, right, that means that L is equal to 0 and 1. If n is equal to 3, L is equal to 0, 1, and 2. And we can actually put if L is equal to 1, if n is equal to 1, L is only equal to 0. So in all of these, right, whether I'm in the first shell, if I'm in my second shell, or in my third shell, I still have a spherical shaped region of space. The only difference between these is that sphere gets bigger. So in the first shell, right, if I was to draw my standard set of axes, in my second shell, you pretend those all crossed in the same point. In my third shell, again, my nucleus is where those are crossing. In all of these, I'm going to have a sphere. It's just going to be smaller when n is equal to 1. It's going to be a little bit bigger when n is equal to 2. And it's going to be bigger yet when n is equal to 3. Because remember, n is defining its extension to space. So that purple region of space that we're drawing extends further away from the nucleus as my value gets bigger. But for all of them, because L is equal to 0, it is going to be spherical. So these are our shapes for when L is equal to 1. Or sorry, when L is equal to 0. When L is equal to 1, that's going to be my P subshell. And what are my values for M sub L when L is equal to 1? Yeah, remember M sub L goes from negative L to positive L. So my values are going to be negative 1, 0, and 1. So I have 3 orientations, which means I have 3 p orbitals per subshell. And these ones are considered dumbbell shaped. And I'm actually going to draw 3 for the same shell. When I did my S-shaped orbitals, right, the ones where my value for L was 0, I only drew 1 because there was only one orientation. If you go back up, let's do that, right, one orientation. And these should all be the same size once I start drawing the orbitals. Again, my artistic skills are limited, but I'm going to do my best. I might have to erase a couple times. But like I said, these guys are considered dumbbell shaped, and I'm going to just make my highlighter a little not so broad. So these are going to contain 2 lobes. So they're going to have a region where the electrons can be that's on either side of the nucleus. And then I'm not going to color over the nucleus. So my electrons can be here and my electrons can be here, but I'm not coloring over my nucleus. And this is going to be really important when we talk about the relative energy of my subshells. So if I go back up and look at my S's here, I colored, right? I'm just doing it again, over that nucleus. I didn't leave a space where that nucleus is. I went right over it. So those are centered around the nucleus. These are not. So I have two lobes. This one I just drew, right? I have two parts and they should be equal. And they are not over the nucleus. So I drew one on my y-axis. I'm going to draw another set on my x. Again, two parts to it. I'm not drawing it over my nucleus. And then another set on my z-axis. Remember, this one's coming in and out at you. So 3 different orientations. It doesn't matter which orientation corresponds to -1, 0, or 1. Just know that I have 3 values for m sub l. I have 3 different ways I can take this and orient it in space, meaning within a given subshell, I have 3 different p orbitals. So we said these were dumbbell shapes. That's the name of them. S's are spherical, these are dumbbell. They contain 2 lobes. The lobes are the regions where those electrons can be, so those are the purple spots. And then they contain 1 node, or 1 nodal plane. And what that is, that's the region where there are no electrons. So if I wanted to slice this right through my nucleus here, there's no electrons there. So that would be considered a nodal plane. So this is the region with no electron density. It's our fancy way of saying the electrons are not going to be there. They are likely located in those 2 lobes. Again, it's probability. Generally, like if you look at pictures online or in your textbook, it's going to draw those borders as fuzzy and not really well defined because it is a probability function, remember. And then similar with the S's, as my value for n gets bigger, then these, right, my dumbbell-shaped regions of space get bigger. So if this is for n equal to 2, all 3 of those would be when n is equal to 2. If I wanted to draw them for n is equal to 3, I would still draw 3 of them. I'm going to leave the axes off this time. I would have my nucleus. Let's just draw the nuclei. But I would actually draw them bigger. So, I want the highlighter. So bigger lobes. I still have 3 orientations, but they're just getting bigger. And then remember, this one's coming in and out at us. So as our value for n gets bigger, its extension into space gets bigger, right? They're still dumbbell shaped. I did a pretty bad job of drawing these, but they just get larger. For L is equal to 3, right? Remember, when L is equal to 3, then, I skipped 2, sorry. Right, we did. Let's just make sure we're all in the same place here. It's hard enough, and then I skip it. So L is equal to 1, L is equal to 2. I can't even count, wow. L is equal to 0, L is equal to 1. We'll slow down here a little bit. L is equal to 2. And then if we go back up to our little comparison between our numbers and letters, when L is equal to 2, these are D. So these would be a D subshell. What are my values for M sub L when L is equal to 2? Good, -2, -1, 0, 1, and 2. This time I have 5 numbers there if I was to count the number of values, so 5 orientations. So there's 5 d orbitals per subshell. So for S-shaped orbitals, right, when L is equal to 0, there's 1. For P-shaped orbitals, when L is equal to 1, there's 3. For our D-shaped orbitals, when L is equal to 2, I have 5 orientations. So 5 different d orbitals per subshell. I'm not going to draw all 5 of them, but if I was, there would be 5. Please, again, look these up. They are in your textbook, and they're all over the internet. So if you just go to Google and Google D-shaped orbitals or D subshell, you're going to get pictures of all of them. 4 of these are considered cloverleaf, and I'm going to draw 1 cloverleaf. So 4 are cloverleafed. So cloverleaf shaped. And I will draw, like I said, 1 of those. And then 1 is considered donut shaped. So we will draw 2 of them, even though there are 5. So my cloverleaf is essentially 4 lobes. So it's like 2 dumbbells. So I'm going to draw here, and then let's draw this one. So on my X and Z. So 4 lobes. So 4 of them are going to be like that. They're just on different sets of axes. So 4 lobes, 2 nodal planes. Remember, our nodal planes are our regions where there aren't electrons. And then the donut shapes, 1. It looks to me like a p orbital wearing an inner tube around the middle. So the p orbital part, so region of space here, and then a region of space here with that lobe in the middle, or sorry, that node in the middle. And then around the middle, there's a region of space. And this is supposed to be like a donut. To me, it looks like an inner tube, but it kind of goes around. When you look up the pictures, it's going to be tighter than that. It's just easier to draw when I make it a little bit bigger, but that's our donut. So this is my cloverleaf. And there's 4 that are similar. They're not exactly the same, right? They're different orientations, not the same orientation, but they all contain 4 lobes with 2 nodal planes. They're just oriented on these axes differently. And then this is my donut, which I spelled wrong up here, didn't I? Sorry about that. Oop, and I spelled it wrong again. Donut's a weird word to spell. A lot of words are weird to spell. So these guys, 5 orientations. My next one, we're only going to go up through F's for our shapes. So L is going to be equal to 3, right? We left off with 2, so L is equal to 3. If we go back up, these are going to be my F subshells. And I'm actually not going to draw any of these, so please look these up. How many would there be if I was to draw them? What are my values for M sub L? Because that tells me how many I would draw, right? Remember, the number of values for M sub L tell us the number of orbitals per subshell. Yeah, what are my values? So -3, -2, -1, right? Everything from -3 to +3, 0, 1, 2, and 3. And if we were to count the number of values that are there, right, there's 1, 2, 3, 4, 5, 6, 7 numbers. So 7 orientations, which means there's 7 F orbitals per subshell, right? There's 7 different ways I could draw it. Most of them are like a double cloverleaf, though there is a double donut. It's not called a double donut, I just call it that. It's like the p orbital shapes, the dumbbell, but then it has 2 rings of electron density around it. So it's like wearing 2 inner tubes or 2 donuts. But for the most part, they're going to have 8 lobes. And then they would have 4 nodal planes. You just keep on doubling every time we go up. With some, exceptions like the double donut. But again, please look up images of these. If I give you a picture of an S subshell or an F orbital, right? I do want you to know what it looks like. You just know that they have 8 lobes. I won't give you the double donut one, and you'll be able to recognize it. I did say that there was a 4th quantum number, and I do want to talk about that one next. So our 4th quantum number. And that is our spin quantum number. And our abbreviation for our spin quantum number is lowercase m with a subscript lowercase s, so m sub s. And of all 4 quantum numbers, this is the only one that's not dependent on the others. I guess except for n, right? The principal one that starts it off. But then L depends on n, m sub L depends on L. M sub S does not depend on L or m sub L. So spin quantum number. And essentially the deal is that electrons spin. So not only do they follow a wave-like pattern as they move, but they're also spinning as they move, kind of like a top. And they can spin in 2 directions. They can spin clockwise or they can spin counterclockwise. And those are my 2 values. So we have 2 values for m sub s. And those 2 values are either going to be plus 1/2 or minus 1/2. And it doesn't matter which is which. One spinning clockwise, one spinning counterclockwise. It doesn't matter which value goes with which direction. Just know that there's only 2 values, and those are the 2 values. So essentially, electrons spin. We actually can say, if we want to sound fancy, electrons possess spin. Basically, they spin as they move. And they can spin either clockwise or counterclockwise, giving 2 values for m sub s. So only 2 values because they can only spin in 2 directions, clockwise or counterclockwise. And then those 2 values again were either plus 1/2 or minus 1/2. Again, it doesn't really matter which is which, just know that they do have 2 different values. So it doesn't matter, what shell they're in. It doesn't matter what is the shape of the orbital, right? What subshell they're in. It doesn't matter if it's oriented on the x or the y axis. They can still only spin 2 directions, clockwise or counterclockwise. So we only have 2 values. We are going to, in the next video, start putting electrons into orbitals. Before we do that, we do need the Pauli exclusion principle. And the Pauli exclusion principle is what's going to tell us the maximum number of electrons per orbital. So Pauli exclusion principle tells us that no 2 electrons can have all 4 of its quantum numbers the same. So if you're going to put them in the same orbital, right? If you're going to put them into the same orbital, they're going to have the same value for n. They're going to have the same value for L. They're going to have the same value for m sub L. So they have to have different values for m sub s, right? They can't have all 4 the same. They can have 3 of them the same, right? They can be in the same orbital. If they're in the same orbital, their values for n, L, and m sub L are all the same, meaning the 4th quantum number has to be different for those 2 electrons. So no 2 electrons can have all 4 of its quantum numbers the same. So if in the same orbital, right, the same region of space, then their value for m sub s must be different. meaning they must be spinning in opposite directions. Since there's only 2 directions I can spin in, since there's only 2 values for m sub s, the maximum number of electrons you can ever put into a particular orbital is going to be 2. Right? If there was 4 values for m sub s, I could put 4 electrons in an orbital. If there was 16 values for m sub s, I could put 16 electrons in an orbital. But since there's only 2 values, there's only 2 electrons. So if in the same orbital, then their value for m sub s must be different. Since there is 2 values for m sub s, then only 2 electrons maximum. We can have less, right? It can be empty or it can be half filled, but 2 electrons maximum per orbital. Again, the reason we want 2, and I do want you to know those reasons, right? I could ask, why can we only have 2 electrons per orbital? And kind of the number one answer that students give me is they'll say, well, there's only room for 2. That's not true, right? The reason we can only have 2 is because there's only 2 ways in which it can spin. There's only 2 values for m sub s. And if I had a third electron in there, now they're going to have the same value for n, they're going to have the same value for L, they're going to have the same value for m sub L because they're in the same orbital, and then they're also going to have the same value for m sub s because there's only 2 different values and I have 3 electrons. So I would be violating the Pauli exclusion principle. The other way you can think about it, and I like this way, the second way, because it just kind of works for me conceptually, is that when you spin electrons, they actually generate a magnetic charge. So anytime, or a magnetic field, sorry. Anytime you take charge and spin it, it makes a little local magnetic field. And that's just physics. Spinning charge generates a magnetic field. So if you spin it in one direction, it's the magnetic field in one direction. It's supposed to be a U, sorry. If you spin it in the opposite direction, it's the other end of the magnet. So it'd be like taking 2 oppositely, like poled magnets, and they would be attracted to each other. If you try to take 2 electrons and spin them in the same direction, it's the same half of the magnet. And if you've ever played with magnets, if you try to get the 2 of the same ends next to each other, they just repel, right? They would repel each other based on the magnetic field. So electrons, remember, have the same charge. So I have one negatively charged particle trying to cohabitate in the same region of space as another negatively charged particle. Based on charge, that they don't want to do that. Why? They want to repel each other. Why would one negative charge like to hang out with another negative charge? They don't, right? But if you spin them in opposite directions, now there's a weak magnetic attraction between the two. So even though they want to repel based on charge, there's a weak magnetic attraction between them. As soon as you spin one in the same direction as the other, now they repel based on charge and magnetic field, and they're never going to stay in the same region of space. So by spinning them in opposite directions, I can actually get them to live, right? Or not me personally, but nature can get them to live in the same region of space. So we could say spinning charge, and it doesn't have to be negative, spinning positive charge does this too. Spinning charge generates a weak magnetic field. And how weak it is just depends on how charged it is. Field. So if spinning in opposite directions, the 2 electrons have a weak magnetic attraction. Right? They still want to repel based on the fact that they have like charge, but the fact that they're the 2 opposite ends of our magnet, they are weakly attracted to each other. So we can keep them in the same region of space. So if I had 3 of them, right, I'm violating the Pauli exclusion principle, but then also just physics, right? They are the same ends of a magnet and they have the same charge, and there's no way they're going to live in the same region of space. I do want to go through a couple examples, and there's some of these in the more homework, so please, if you're not doing those, do it. It's good practice. So just a couple example questions that are typical for me. So we could say, what are the allowed quantum numbers and we'll just do values for N, L, and M sub L. We'll leave off M sub S for now, in the third energy level. So if we're in the third energy level, what are my possible values for N, my possible values for L, and my possible values for M sub L? So if we're in the third energy level, that means that N is equal to 3. So that's my value for N. Remember that my values for L go from 0 to N minus 1. So for L, I get 0, 1, and 2. Right? N is equal to 3. 3 minus 1 is 2. So everything between 0 and 2. So 0, 1, and 2. And then my values for M sub L do depend on L, and they go from negative L to positive L. So we're going to have a different set of values for every value of L. So here, M sub L is going to equal 0, because there isn't a positive 0 or negative 0, right? It's just 0. Here, M sub L is going to be everything from negative 1 to positive 1. And then when L is equal to 2, M sub L is everything from negative 2 to positive 2. So negative 2, negative 1, 0, 1, and 2. So this would be the answer to my question. N is equal to 3, L is equal to 0, 1, and 2. And then for M sub L, I have to give 3 different sets of numbers because I have 3 different values for L. 0, when L is equal to 1, is the same orientation as 0 when L is equal to 2, but again, the size is different. I do want the different values. So for each value of L, give me the set for M sub L, if I'm making sense. I hope I am. Another type of question I would ask, what are the allowed quantum numbers And again, right now, I'm just going to ignore M sub S. So N, L, and M sub L for a 4p orbital. So be careful on this one. The difference between this question and the one before is on this one, I'm just giving you the energy level. Here, I'm also giving you the subshell. So this is this sort of notation. If there's a number and then the letter, this is going to be my shell. This is going to be my subshell. And this is why we're using letters for values of L instead of numbers. Otherwise, I would do like 4 and then a 1, and it would look like 41, and it's confusing. So if you have a number followed by a letter, that number is my shell, that letter is my subshell. So if I'm saying 4p, n is going to be equal to 4 because my shell is 4, right? And then my subshell now is not 0, 1, 2, and 3, right? It could be, but it's not, because I'm stating very specifically in this problem that my subshell is p. And remember, if L is equal to 0, it's S. If L is equal to 1, it's p. So L is only equal to 1 in this problem because I'm designating p. So in this problem, I just said third energy level, so we had all of these possibilities for L. Here, I'm saying that my subshell is p, which means I only have this one possibility. If I didn't put the P there, then it would be 0, 1, 2, and 3 because I'm not being specific, but I am being specific in this problem, so be careful. And then my value for M sub L, since I only have one value for L, I'm only going to have one set of values for M sub L, and that's going to be -1, 0, and 1. So this would be my answer for this problem. So just be careful. Am I giving you a subshell in the problem, or am I only telling you the shell? Right? If I'm only telling you the shell, then we have all of these possibilities, and then we have a different set of values for M sub L for each subshell. If I'm giving you a very specific subshell, right, I only have one subshell, I'm only going to have one set of values. M sub S is always -1/2 or +1/2, which is why we're not including them here in this problem. Another example that I like to ask, and this is one of my favorites, is why are there no p orbitals in the first shell? Similar question I could ask, why are there no d orbitals in the second shell? Other similar questions I could say, why are there 3 orbitals in a p subshell? And all of our questions here have to do with quantum numbers. For those that have had chemistry before, which should be all of you, right? You've done electron configurations before. I could give you carbon and say, write the electron configuration, which is what we're building up to, and you would tell me 1s2, 2s2, 2p2. But you probably don't understand what the 2 is and what the p is and why there's only 2 when it's s and why you can go up to 6 when there's p, and that's what we're trying to get at here, right? I want you to understand what that is, not be able to just memorize where stuff is on the periodic table and write down numbers and letters, right? I could train my mom, who knows nothing about chemistry, to do that. This is college, right? We want to understand what this means. And those coming into this class with, you know, the baseline knowledge that you have, they usually give me periodic table answers. So if I say, why are there no p orbitals in the first shell, a very common answer that I tend to get is because, well, on the periodic table there isn't room. Okay, the periodic table, just be careful here, is never going to be our answer. The periodic table is a tool that allows us to help kind of remember why things are, but it's never going to be our answer. Right? Electrons do not consult the periodic table to see what orbitals they should be in. So the answer to these questions will never, ever, 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 ever be your periodic table. So why are there no p orbitals in the first shell? It has to do with quantum mechanics, right? Remember, this is a mathematical model. Our answers are going to have to do with those quantum numbers. So if we're in the first shell, what is my value for n? Right? N is going to be equal to 1 if we're in the first shell. If I'm in the first shell, what are my values for L? L is only going to equal 0, right? L only is 0. And our reason for that is that L goes from 0 to n minus 1, right? In this case, n is equal to 1. So in the first shell, L goes from 0 to 1 minus 1. So 0 only. To have a p subshell, right? If a p subshell L equals 1, L does not equal 1 in the first shell, or cannot, we should say. Right, remember, if L is equal to 0, it's my S. If L is equal to 1, it's my P. So to have a P subshell, L has to equal 1. If I'm in the first shell, L is only 0, right? 1 minus 1 is equal to 0. So it can't possibly be equal to 1. It can only be 0. That's really just the entire answer, right? If I'm in the first shell, L is equal to 0. It can't equal 1, which is what it has to equal to be P, because 1 minus 1 is 0. 1 minus 1 does not equal 1. That's the answer, right? Why are there no d orbitals in the second shell, right? If we want to do a similar sort of answer, if I'm in the second shell, n is equal to 2, which means L equals 0 and 1. If we go back up to this little list we were making, to have D, right? L has to equal 2. L does not equal 2 in the second shell. I had asked, kind of in passing, I said another type of question I like to ask. Why are there 3 orbitals in the p subshell? Remember, the number of orbitals had to do with my number of values for m sub l. So if I'm in the p subshell, right? L is equal to 1. Again, that's going back up to this. When L is equal to 1, m sub l equals -1, 0, and 1. 3 orientations, 3 orbitals. Again, a common answer I'll get to this is they'll say, well, it holds 6 electrons. It holds 6 electrons because there's 3 orientations, not vice versa, right? If there's 4 orientations, it would hold, right? If there's 4 orbitals, it would hold 8 electrons. So the number of electrons it can hold is based on the number of orbitals, not backwards. So be careful for reverse logic, right? There's 3 orbitals because there's 3 values for m sub l. Because I can put 2 electrons per orbital, my p subshell can hold 6 electrons.